Hi everyone and welcome to another lecture. So in the past lecture we saw how we can define a matrix in Mathematica and how we can do different kind of operations with it. So today we are going to see more of it. The first thing we're going to do today is that we're going to take the Hermitian conjugate with Mathematica. So let's get started. So define a matrix. First let's call it small m. Let me zoom out a bit. Yes. So let's write a matrix with complex entries as well. And let's take the last element to be 0. For simplicity and less typing, I am taking a 3 by 3 matrix, so I want to suppress the output, and now I want to evaluate what is m dagger, that is its transpose and conjugate. So to do that you just have to type transpose, and if you just click on here you can see more options. There's a lot of options. So we are looking for transpose conjugate, right? So transpose conjugate. Okay, so it's not transpose conjugate, it's conjugate transport. As you can see, it's not transpose conjugate in Mathematica, rather conjugate transpose. So if you click it, put your m, and if you just run it, and let's say I want to show it in the matrix form, yeah, there you go. So this is how you can easily go for transpose conjugate as well. And again, if you want to calculate the determinant, the inverse, all you have to do, you just have to type all the things in. But what we want to do now is that we want, for this matrix, we want to know the eigenvalues and the eigenvectors. So let's type eigen. As you can see, eigenvalues, eigenvector, eigensystem, and all the options are here. So just type eigenvalues, you put in the matrix m, click it. So these are kind of suppressed output, so that's why Mathematica is showing these things in this way. And you can see that you can plot these things in complex plane as well. So let's click on that, and you can see that in the complex plane it's a list plot, and Mathematica used some commands, and these 3 eigenvalues have been plotted as well. Now let's go for eigenvectors. To do that, just type eigenvectors of m, you want to know them, and this will be your eigenvectors. Our matrix was not that good, so that's why it has a huge output. So let's define another matrix, and this time let's take it to be a 2 by 2. Let's say I want to have 1 0, another one as 0 comma minus 1. And since this is a diagonal matrix, so you can easily understand this eigenvalues will be 1 and minus 1. So I want to have the eigenvectors, so eigenvectors will be, yeah, this is 0 1 and 1 0. See, this 1 0 and 0 0 minus 1 is just the poly z matrix, and that's why you should get 2 eigenvectors, that is one of them as being the positive z axis and the negative z axis, and here you are just getting that. So this is how you can use Mathematica for determining eigenvalue and eigenvectors. And note that since we have also learned how to use inverse of a matrix, so you can also solve linear systems for different purposes. But if you have a very big chunk of data, then you have to use something called a linear solve. So if you just type linear solve and you want to know how this works, it says that finds an x that solves the matrix equation mx equals to b, right? So this is similar to taking an inverse and then multiplying it with a column vector. So you can even use this command to do the linear solve thing. And let's take now a 4 by 4 matrix, so let's call it capital A, and you have to have 4 lists, and then you have to enclose them with a bigger list, and I put third brackets by mistake, so I have to get rid of them. Okay, so let's call this 1 2 3 0, and for the second one I want to have 0 comma 2 comma 7 comma 6, and then I want to have, let's say, 0 2 1 9, and finally I want to have 1 2 5 7. Okay, so let's suppress this. But now what you want to do, like you used to do in linear algebra, you want to find the row reduced form. So type row and it says row reduce. If you again put your cursor over here, it gives the row reduced form of the matrix. So just put A. This is your row reduced form, and you can see this is a very simple output. It means that all these variables are over here, they can be uniquely solved. So this is the reduced row echelon form, and Mathematica just simply solved all of them. So you can even array plot this thing. If you just type array plot, you can see all of this black box are representing a 1. You can even customize this array plot, and let's say you want to have mesh. You want to have mesh, let's say all of them. If you just do that, you see this is like a box thing. So this kind of array plot or list plot, they are very helpful in visualizing big chunks of data. You can even add a color function. Let's call the rainbow. You can see that all the zeros are here is denoted as violet and all the ones as red. So to know that, you just have to type plot theme. Again, you can see this plot theme works always. So detailed, give a detailed thing, and you can see that these colors will represent which number that you are having over here. So let's try to do a thing. Let's try to, now since this array plot looks really nice, we want to have an array plot of our matrix A. So we want to plot A, and then we want to customize it. So we want to have a color function. We want to, let's say I want to have this rainbow. Then I want to have my mesh. I want to give all of them a mesh. So ultimately what I need to do is just to type plot label, sorry, not plot label, plot theme, and let's give them details. You can see that the 0 is corresponding to these places, that is the violets, this one and this one. This red is above 8, and you can match the colors and you can visualize this matrix like this. In fact, this can be used in other ways, and possibly we'll see them in the future lectures. So this is how you can do all the things about matrices. But before I finish off, I want to explain and discuss something called the powers of a matrix. Powers of a matrix. So let's say you have a matrix A, that is this matrix over here. Let's write this down again. Again, run this. Okay, everything is fine. But let's say I want to know what is A times A to the power 20. That is, I'm multiplying the matrix A 20 times. So if you recall that I discussed A dot A will give you A squared, that is A with A. That is, if you want to have a standard matrix multiplication, and you have to do it by A dot A, right? So now you might ask that, do I have to type A like 20 times? That is, I have to A dot A dot A. No. Mathematica has a built-in function that deals with powers of matrix, and it's called matrix power. If you type matrix power, you can see that it will take a matrix M and it will raise it to the power n. So let's take our matrix A, and let's raise it to the power, I don't know, 20. So let's see, and I want to see the output in the matrix form. It will be something huge as expected. So how about 2? That means a squared. Yeah, pretty simple, right? And by using these powers, you might ask right now, can I use Mathematica to compute exponentials of a matrix? So that means you have an exponential function e, and in the power of e you have a matrix, and these are pretty helpful when you are dealing with high energy physics and so on. So to do that, all you need to do, you have to type matrix exponential. So if you just have matrix exp, that means exponential. So this will gives the matrix exponential of m. So since this is a 4x4 matrix and it's pretty huge, so let's try to see what happens. It might take a long time, but you can see that it's not taking a long time for Mathematica to do this, and this output is really huge. And there are also these root sums and so on. So let's try to full simplify this whole thing. Also, I want to see them in the matrix form. Yeah. So this is our exponential thing that is coming up from matrix A. But what about a very simpler matrix, that is a 2x2 matrix that we discussed, was this one, n. So let's again run this, and I want to have matrix exponential. Matrix exponential of n. Let's see. You can see this is quite simple. This is, one of them is e, one of them is 1 by e inverse. So this is quite nice that Mathematica really computed them in really fast. So yeah, this is it. And you can see that you can also have this matrix plot, display as, and lot of things. Now, using the matrix exponential, we saw that Mathematica can deal with it, but Mathematica can even do a matrix logarithm as well. So you can type matrix log, and let's say I want to have the log, that is, this means you have log of n. So in the log function, you don't have a number anymore, you have a matrix. So if you run it, this is the output. So this is how you can easily deal with any kind of huge heavy calculation that involves matrices. And in fact, you can also see that Mathematica also tells us about the matrix rank as well. So if you just type in a matrix and you want to know its rank, just do it over here. Use matrix rank, input the matrix, and so on. So I want to know about my matrix rank, and let's take our matrix A. That was this huge matrix over here. It has a rank 4. And now let's talk about something called a tensor product. So I have two matrices, let's say A and B. I mean A and N. That is a 2x2 matrix, and another one is a 4x4 matrix. So can I take a tensor product of them? Let's try to see. So A comma N. You type tensor product. You type in your inputs. Let's see. Yeah, it does that. So as you can see, there are dimensions, there are transpose, there are flatten, array depth, and if you type in more, matrix by blocks, if you do that, it will use a command called array flatten, and this will be it. But what if I type matrix form right now? Will it work? Yes, it will work, and this is coming as a block by block matrices. And from our theoretical knowledge, we can expect that I have a matrix of 4x4, I have a matrix of 2x2. So what is happening here is that all the 2x2 matrices will get multiplied with the elements of the 4x4 matrix, right? That's what's happening, because A is in first, N is in second, and you can see that this is the result. Because notice in A, so let me just show you A in the matrix form. So this is A in the matrix form. Just ignore this thing, because since this is in the matrix form, Mathematica is not evaluating this line, so you have 1 over here. So instead of 1, you now expect n, the n matrix that was our Pauli Z matrix, it will take its place. And here 2 will get multiplied with this Pauli matrix, is 3 and 0 and so on. So finally you have this chunk. So this is how you can easily evaluate tensor products as well. In fact, if you have 2 column vectors, let's say B equals 1, 0, 0, 1, and after that you have a C that is just a 2, 3, and finally you want to have tensor product B, C. This is your result. You can find it very easily, and you will just type matrix form. You can see that if you tensor product B and C, this will be our result. So yeah, this is how you can easily do it. But there is something to note here, because it's saying 2, 3, 2, 3, 0, 0, 10. So in the matrix form, it's like it's replacing the rows, but in tensor product we expect that first 2 will get multiplied with all the elements of B, then 3 will get multiplied with all the elements of B, right? So what is happening over here? So you see that if you want to have 2, 3 first, that is on the left side theoretically speaking, and 1, 0, 0, 1 on the right side, you have to put this command C, B. So this means C is on the left side, B is on the right side. So now let's do it. Yeah. So there you go. So this is how you can easily deal with tensors as well. That is some elementary long matrix multiplications and all that. So this will be it for today, and thank you.